Hi, I'm Gabriel, and I worked with Cristina Herrera on using different model selection techniques to garner whether or not a planet exists. So the story starts with Vogt et al. Claiming that an exoplanet exists in the habitable zone of another star, which we'll call Planet G. He used high-res and HARPS data to make this conclusion and made several flaws, missteps along the way. Used a periodogram in order to decide that there were 6 planets and assumed perfect residuals. Used a p-value to make this 4.7 sigma confidence conclusion that this planet exists. And he used reduced chi-squared on a nonlinear model. So ultimately, follow-up data from HARPS refuted the original claim. And the big question is, could this have been avoided if Vogt et al. Used different statistical techniques? Which is what we're going to be trying to find out. So here's the naming conventions for the models. I won't go through it rigorously, but in essence, there's 6 models, and the first 4 we're pretty confident about, and planets F and G, we are still trying to figure out whether or not they do or do not exist. So we're going to start by calculating the base factors using mainly the BIC and the AIC. Reduced chi-squared was used in the original paper. The benefit of these metrics is that they penalize for complexity. And there's no reason to prefer one model over another, so we can assume that the base factor is equivalent to the odds ratio. So the premise of this is that we will start by looking at the null model, which is model 0, and compare all the other models to it. And then, in this case, model FG performs best. So we compare all the other models to that one. And as you can see, the base factors are all less than 1 in this case, meaning that model FG is preferred. It's a similar story for the AIC, as you can see. And this leads us to conclude that, as Vogt claimed, model FG is the most likely model. Now, there's drawbacks to these methods as well, which is one, we're looking at a nonlinear model, meaning that we have to only guess K, which is less than ideal. There's also no consideration for the priors or likelihoods, so is this really Bayesian? Now, we would like a better way, and there's another option. That's using cross-validation. So we use a leave P out method, where P is 20% of the available data, meaning 80% is used to train and fit the model, and then the rest of the 20% is used as a validation set. We calculate a chi-squared of each model using the validation set as well, and the reason why we don't use the BIC or the reduced chi-squared is because that would be double dipping on penalizing for complexity. The method of cross-validation intrinsically penalizes for complexity. So we repeat this 10,000 different times using different training and validation sets. You can see the 50th iteration here on the right. And in each iteration, we add 1 point to the score of the model with the lowest chi-squared. In this, it produces these results. As you can see, model FG wins out enormously again with a very high odds ratio of 51. And that leads us to conclude that the 6-planet model, model FG, is the most convincing one, which is in line with Vogt's original claim. Now, there's plenty of advantages to this method. It's a useful way to predict how your conclusions would perform with the presence of future data. You don't have to compute evidences, and the priors don't matter. However, leave P out is non-exhaustive. You must sacrifice data along the way, and it's computationally expensive. And that's where this begins to fall apart. So the big conclusion is that it's important to keep in mind the limitations of the methods you use. And with that, that's all I have for you. So thank you very much.